Welcome to the instructional video for Lab 8 from Astronomy 20. This is called Motions of the Sun, and that's what this lab is all about. Now, this lab is primarily based on the Nebraska Astronomy Applet project, one of their simulations, and that is called Motions of the Sun. And here's the student guide, and you can see some upfront similarities, but I have very much made this particular lab my own. I have added some links, I've added some questions, and further exploration. All right, so let's get into it, because in this video, I want to go over the lab as a whole, go over the 22 questions that compose the lab, give you some tips, and just talk about the overall form and flow of the lab. So you can see the first question is referring to the background information within the applet here, and that would be the sidereal versus synodic. This talks about the difference between those two types of days and years, although we actually call it the tropical year and the sidereal year, okay? Which will come up in question 2. But as far as question 1 goes, there are a number of questions. I'll go ahead and read number A here. If the Earth revolved more rapidly, its sidereal day would be blank. And here you're going to put whether it'd be shorter, the same, or longer. And you should be able to get that information out of this background reading here. And notice that you can scroll through and get a little bit more about that information, including leap year, which is described as optional here, but certainly is a topic that we'll get into, although not exactly called the leap year, but we'll talk in detail about something called the equation of time and the analemma, which is covered within the simulator. Now, as far as further background reading, there's a section on seasons and the zodiac, which will come up later. Now, this is not a full-fledged simulator, but it is controllable. So you can actually grab the screen here by clicking on it and move it around. This is going to change your perspective, although it's not going to change the date. You can see here the date is set at January 1st, but if you grab the red controller here, you can actually adjust the date, and that's going to have the sun progress through the different constellations, because the constellations remain fixed over time, at least fixed over time of millions of years. So over 1 year, there's no movement of those distant stars which form the constellations, so the sun appears to move through them. That's the concept of moving through the zodiac. I'll get back to that in a second. But let's go ahead and look at our other background information here. We actually have the simulator, and then we also have something called the meridional altitude, which talks about how to calculate the height of the sun above the meridian. And you do have another little mini simulator here where you can take a look at some key points here, such as the poles with how they appear in the local sky, and so on. All right. And it gets into ideas of declination. All right, you can hide declination. You can hide the poles. Here you have let's see, this is called the celestial equator, of course, right? So you can include the celestial equator or you can hide it. All right, and these would be the celestial poles. And this you'll all see on a couple pages within the lab itself. I'll go ahead and give you a quick preview. So if you go down to page, that would be, looking for a page number. Actually, don't have the page number visible right now. But when you get down to this page, there is a couple of figures that I included. These are not in the original version of the student handout that really, I think, do a good job of showing some key terms in referring to how objects are located in the celestial sphere, which is this figure here, and how they're located in what's called the local sky. And that's what you actually see when you look up at the night sky, okay? Or, well, maybe you look at the sun, because after all, this is all about the sun, and we're not going to be talking about following the path of stars. We're just going to be exclusively talking about following the path of the sun, which honestly is more complicated than following the paths of the stars, because remember, the stars just remain fixed in place. All right, so those terms, by the way, are the azimuth and altitude. That the azimuth is measured relative to the north. That would be the north, direction from where you're standing, that the north that a compass would give you. And then you measure an angle relative to that north direction. That is called the azimuth. Okay, and the altitude, also measured as an angle, is the angle above the horizon. Now the horizon makes a circle, right? And if you're standing on perfectly flat ground, then the horizon is just that, a circle that you can see around yourself when you're wrapping at full 360 degrees, and then up above that horizon to some point is the altitude. To give you some context on that, if an object, such as the star, was all the way directly overhead a special point known as the zenith, it would have an altitude of 90 degrees, okay? Now, if the sun crosses the celestial meridian, then that also is a particular point. Although the sun may not cross the celestial meridian at the zenith, it could cross the celestial meridian at a lower altitude. Okay, a lower altitude measured relative to the horizon. It need not pass exactly through the zenith. In fact, it rarely does. Now, what is the celestial meridian? The celestial meridian is a point that in your local sky that goes exactly from due north, as a compass would read, to due south, okay? And that is really the single context in terms of a line that connects north to south. All right. Now, as far as measuring things in what's called the celestial sphere, we have different terms because it is a different reference. All right. So when you're measuring things in the celestial sphere, it is more similar to measuring things as we do on the sphere of the planet. Of course, those are measured in latitudes and longitudes. But the equivalent within the celestial sphere are not called latitudes and longitudes for a number of reasons, owing to the fact that, of course, we're moving, we're spinning, and so there's not the same idea of a fixed reference. It's not like with the planet where the poles are fixed and we've chosen this idea of the prime meridian to be fixed in place. Instead, with the celestial coordinates, we still have chosen certain things to be fixed in place. As we can see, the vernal equinox is essentially plays the role of the prime meridian. It is a fixed longitude. And then as far as latitudes, we have the very equivalent ideas of a north celestial pole and a south celestial pole. Now, those poles are exact projections of the Earth's rotational poles, the North and South Pole, okay? Now, the thing is, though, that the vernal equinox is a little bit more of an abstract idea. Which way does the Earth face relative to the vernal equinox, right? Well, different parts of the Earth are facing towards the vernal equinox at different times of the year. So when we talk about the measurement that would be the equivalent of longitude, we actually call that right ascension. And that really kind of refers to the fact that it is a moving amount, right? It depends on the moment that the measurement is made. It is constantly changing in time. And to really highlight this fact, right ascension is actually measured in units of time. Now, 24 hours of right ascension is equivalent to 360 degrees in angular measurement. So there's a direct correlation there, but regardless, we use a time measurement to highlight that it's always changing. All right, it's just to say that an object in the sky is moving, right? At a certain time of the day, we see it rise up above the east and then set in the west. That's the apparent motion. That is a manifestation of Earth's spin, right, along its axis. So that's the idea, that location, that right ascension, since it is constantly changing, is then measured in time. All right, but that will give us its exact coordinate at that moment in time, which of course is very useful. Furthermore, the equivalent of altitude in the local sky within the celestial sphere, or maybe, as I said a minute ago, a more apt comparison is the equivalent of latitude from the coordinates on the planet to the celestial sphere is called declination. All right. Now, declination of 90 degrees, because it is measured in degrees, would be exactly at the North Celestial Pole, and a declination of negative 90 degrees, or sometimes called 90 degrees south, would be at the South Celestial Pole. Okay, so those are the ideas of how we coordinate locations of, in this case, the sun, but it could be used to coordinate anything, the moon, a star, a planet, anything that we can observe from the surface of Earth. Okay. Now, there are a couple other special lines that show up here within the celestial sphere. One of them, no surprise, I'll zoom in a bit here so you can clearly see it, is the equator. This is exactly a projection of Earth's equator. Okay, so the same way that we have an equator that is exactly halfway between our rotational poles, north and south, the celestial sphere has an equator as well. Okay, that is equivalent to 0 degrees declination, right? And you can go up to positive 90 or negative 90 relative to that celestial equator. What's interesting, though, is that the celestial sphere has this jaunty belt, which is the ecliptic, and that's because of Earth's tilt. So what is the ecliptic? It is the apparent path of the sun through the celestial sphere. So just like we are seeing in the zodiac here, we could see the sun moving through all those different constellations. If we were to track the sun and see it move along the ecliptic, well, that's exactly what it would do. The sun would move along this red line over the duration, and would complete a circle over the duration of 1 year. Okay, but what type of year? Well, I'll take that as a good transition to segue back to the first page. And by the way, yes, I jumped ahead to talk a little bit about these terms, but really they're relevant at any point in the lab. So if we go back here, you can see that in question 2, I ask about the difference between a tropical year and a sidereal year, okay? I say that the background information provides very little detail about the difference between the tropical year and the sidereal year, but there's a sidereal year mentioned there. There is a excellent video that does go into some more detail. I'll go ahead and show you what that link looks like, and you can follow the link from the lab itself. So let's go over here. So this is the video that is linked. Now it's 9 minutes and 27 seconds long, and I highly recommend you watch the whole thing, but you're not going to be able to get all the information up front. It is incredibly information deep. But what you can get is what the one thing I asked for in question 2 is summarize the difference between the tropical year and the sidereal year, and specifically talk about which one is shorter and why. All right, so I said, well, I say which one's shorter. I tell you that the tropical year is 20 minutes shorter than the sidereal year. Why is that, right? What is the key difference between these two types of years? And, of course, by this point, you have already understood the difference between the solar day and the sidereal day, and that will maybe help you in understanding that sidereal always means the same thing. Sidereal is this idea of motion, Earth's motion, relative to a fixed background. What fixed background? Well, you might as well call it the zodiacs, because really it's the fixed background of very distant stars. But in reality, a lot of what we care about isn't the way that the Earth moves towards those distant stars, but instead the way that the Earth moves relative to the sun, right? This life-giving, energy-giving body at the center of our solar system. And likewise, when we talk about the motion of the moon, we can talk about the moon in terms of its sidereal orbit around Earth and in terms of its solar orbit, also called its synodic orbit, okay? Which one do we care about more? Well, you guessed it, the synodic or solar orbit, okay? Now, as we continue on, let's take a look at question 3. Now, question 3, again, talks about the solar day, and it talks about the fact that the sun does not exactly return to the meridian after a 24-hour period of time. And why is that, right? Why does the solar day not last the exact same amount of time throughout the year, right? Because it's one thing to say that the solar day and the sidereal day are not equal to each other. And to give you a hint at that, we can take a look at this figure, which does a wonderful job of illustrating why one has to be longer than the other, okay? But what I'm saying here in question 3, and what I'm talking about right now in the video, is actually an extension of that idea, saying a bit more that not only are they different, but one of them, okay, the sidereal day, totally constant, totally reliable. The solar day not. The solar day actually changes throughout the year. Why is that? Okay. Well, to start to explore that, we have an idea that I return back to many times throughout the lab, finally culminating in the last few questions around question 20. And this is the idea of the path that the sun takes through the sky if we were to track it over a year. Now, this figure 8 shape, okay, which I'm sure I will give away its name at some point, but here I actually ask you for its name. All right, and I won't say it right just yet, right? But then in part B of this question, I go on to say, right, an example of this figure 8 shape is shown in the figure, right, taken here at some northern latitude location with something that kind of looks like Stonehenge, but isn't actually, Stonehenge in England, but certainly is probably at a similar latitude. Okay, each bright dot is the sun. Okay, now obviously this isn't the sun over the duration of a single day. Instead, this is the duration of the sun over many days, right? And I say, over how many days would a photographer need to return to the same spot at the same time of day for a photo in order to create a composite photo like this? Because what we see here is, in terms of, using traditional film photo, you could just use the same piece of film and just expose onto that same piece of film over and over again, or you could use a similar digital effect where you're essentially overlaying images on top of each other. And what you're seeing then is the sun, right, put back on top of itself many times throughout the duration of a long period of time, enough to complete a cycle where the sun appears to track a figure 8 through the sky. Okay? And then in part C of the same question, question 4, on each day that a photo of the sun was taken, at what point was the sun in its path from sunrise to sunset? Okay? Because if you want to be consistent and actually get the right shape, you have to make sure that you take it at a certain time of day. What time of day do you think that is? Okay? So I mentioned the Zodiac Explorer a couple of times. Question 5 is the question I hinted at, which is the one that gets into some specific questions. Now, these questions are similar to the original version of the student handout. I did make some small changes to them, but you can see they all revolve around using this little tool here in terms of changing our view and looking at what stars are going to be obscured by the sun and which stars are going to be visible. Because, just to give you a quick reality check here, you can see that the sun is actually shown, right, as a bright white circle. And so that means that all of these constellations that are sort of washed out in this, this lit up manner, those are the constellations that are quote unquote visible at day, right? Now, of course, right, do you see stars during the day? Not normally, right? There's one very rare exception where you could, and I ask about that, all right? In fact, it says right here, total solar eclipse, right? Oh, there you go. So, but for the most part, you're not going to see stars during the day because the sun is so bright. Of course, you can't see stars, right? You're lucky to see, a nearly like a quarter moon or a waxing gibbous or a waning gibbous moon, right? These phases of the moon, which are up during the day, and they are visible, right? But that's because the moon is quite bright compared to stars, okay? But you're not going to see any stars during the day or any planets for that matter. And that means that during this time of the year, which would be, the 1st of January, these constellations like Sagittarius, Capricornus, and Scorpius would be invisible, right? Whereas at night, you'd be able to see the constellations that are exactly across on the other side. Now, what time of night? Well, think about it, right? Because this represents the sun's location at noon. So constellations that are exactly opposite of it are constellations that are passing through the meridian, right? So because that's the midpoint in their rising and setting cycle at midnight, exactly 12 hours later. Okay, so hopefully that will give you some context of how to answer the questions here. So in other words, this ring here represents the light and darkness within a single day, and then we can change where the sun is located to get an idea of what different days look like throughout the calendar year and what different constellations are visible and what times they are visible. All right, so then we're going to move on and talk about the meridional altitude and sun paths, okay? So this calls us to look at the explanatory material, which I had mentioned briefly over here, all right? So this is going to use this information here, and it's going to ask you to consider some particular locations on Earth. Okay, so let's take a look at the first one here. So complete the following tables on meridional altitude. You are encouraged to check your answers with the Meridional Altitude Explorer, but you should make every effort to solve these problems yourself. That's the best way you can get a handle on this material, is thinking about it, trying to reason it out before you just default to having the simulator do it for you. Now, there are some things that are complicated enough where we kind of almost need to explore the simulator first to get some idea, but this is not particularly one of them. All right. Now it says here that note that part D is completed for you. And so if you scroll down here, and this I included from the original version of the student handout. I'm not sure why it wasn't part A, but for whatever reason, it's part D. And you can see this one's already filled in, so you don't have to complete this one, okay? But let's take a look then. The locations are, first, some very straightforward locations and kind of fundamental ones. The North Pole, right? That's on Earth. That would be a latitude on Earth of 90 degrees, okay? Now remember, that would be equivalent to a location on the celestial sphere with a declination of 90 degrees, okay? And that's actually where the North Star is, right? But again, we're mostly interested about the sun here in this lab, but regardless, it's kind of interesting to think about. Then we do have an object we're to consider, which is Betelgeuse, which has a declination of 7 degrees. So what is its meridional altitude? In other words, how do you relate the declination and latitude? Okay, that's the idea. You're essentially going to come up with a formula, if you will, to directly relate meridional altitude to declination of any object, in this case, some star, and your latitude on Earth. And if you read through the information, it does spell out how to do it. and then you should be able to answer this information and complete little figures like this one here for D, which I'll talk about a bit more. All right, so take a look here. Here we have a location on Earth that isn't the equator or the poles. It is a city in Chile at a latitude of -20 degrees or 20 degrees south. And the object we're interested in is Sirius. Now, Sirius has a declination of -16 degrees. Now, declination is fixed, okay? Right ascension varies over the duration of any given day, right, is a constantly changing variable. It's the instantaneous location of that object in the celestial sphere, relative to the equinox, or rather relative to the vernal equinox in particular, right, the equivalent of the prime meridian for the celestial sphere. But declination, again, doesn't change. So Sirius, a very bright star in the sky, always has a declination of -16 degrees. So then we can then do a calculation here to calculate what its meridional altitude would be for an observer at this city in Chile. Okay, and we do that by taking looking at 70 degrees. 70 degrees represents the angular distance from the nearest pole, because the poles are 90 degrees relative to the equator. Here we have that this city, which I'm not going to try to pronounce, is 20 degrees south of the equator. Therefore, 90 minus 20 is 70. Then we add the declination because it's negative, so it's on the same hemisphere. And what we get then is a meridional altitude of 86 degrees. Okay, so that's going to show us the location, right, of our star. Okay, so then we can locate that star. We can actually show its location in the following figure. All right, and we're going to see that it's going to show up, all right there at 86 degrees, right? 86 degrees relative to the north direction. And so it's almost at 90, right? Just a little bit short of 90. And Z is the location of the star, okay? And there we have it, right? There we have a way of locating this particular object, right? Its location in the celestial sphere is shown in blue. Here we have the actual location of the observer essentially in the celestial sphere, and then we can use that relationship to find where they would see this star, okay, and where they would see the star relative to their horizon, okay, because that's what meridional altitude is all about. Okay, because that is the point where this star passes through the meridian, because the star is going to have all different types of altitude, right? It's going to, of course, rise and set like any object, as again due to Earth's rotation, but we're asking for its altitude at the moment it passes through the meridian, this line that connects the compass north to compass south in your local sky. Okay, all right, so hopefully this gives you some background, and of course this will all make sense, more sense that is, as you continue to explore this page here within the the lab. Okay, now we're going to get on to the main simulator, so I'll go ahead and go back here and start at the simulator. Now this is what we're going to use for the rest of the lab, other than a couple of extra links for some more explanation. So this first page here is all background information, which I already kind of jumped ahead and talked about some of the key things, the ideas of azimuth and altitude, as well as right ascension and declination. Okay, but there's some more information here too, which of course I highly recommend you read over. But let's take a look at question 7. All right, so we're going to set up the simulator for Normandy, France, which has a latitude of 49 degrees. So that's one thing that we're going to do quite a bit in the simulator, is we're going to take a look at the different locations, and then vary those locations, and then look at what we can observe. Although I just realized I opened the wrong simulator. So please let me close this one. This one actually doesn't have as much use, although I will point out one really good use of the simulator, which I didn't mention before, is with that very first question. If you feel like you're not sure about whether a particular change would affect the sidereal day or solar day just based on the background reading, adjusting this this simulator or exploring the simulator could be a really good way to get a further handle on that information. But actually, I have to go one more page, all right, to this simulator. This is the one we're going to use throughout the rest of the lab, right? I opened it up and didn't realize I'd opened the wrong one. Okay, so this is the key simulator, right? This is the Path of the Sun simulator, and this is the one where you can actually set different locations, which you can see because you can actually see that we have a line here where we can set our latitude. Now there's no ability to set longitude, and I bet you could guess why that is. That's because longitude is just a matter of when you're going to see something rise and set, but that's not going to affect what you're actually going to see, right? In other words, anyone on the equator is going to observe the same type of day, but they're just going to observe it at different periods, right? They might observe that same type of day, a few hours later, but it's the same. The sun will take the same path. So everyone along a particular latitude will see the sun as well as stars take the same path. Okay. The only variation is when they see it, and there's only be a time delay of up to 12 hours, right? But here, right, we're not interested in that. We're only interested in the overall behavior, so we can only control the latitude. Right, so getting back to the latitude we want to set it at, which is 49 degrees north. Let's go ahead and set it. Now you can actually exactly set it by typing it in. So if you type in 49 degrees north exactly, then there's going to be some questions about some key dates: the summer solstice, the autumnal equinox, and the winter solstice. Okay, now you can look up these dates, but in general, the summer solstice is going to be, well, actually, the equinoxes are always exactly on the 21st. So in terms of the equinoxes, we're going to have March 21st is exactly the vernal equinox. If I get over there, okay? And then likewise, we have that September 21st is exactly the autumnal equinox. Now, the thing is that the solstices will vary between the 20th and the 21st, but let's just take them as the 21st, okay? So when I ask for the summer solstice, go ahead and just put that down as June 21st, okay? And then, of course, the winter solstice is December 21st, okay? Which is not asked about in this particular question, or actually it is. The one that's not asked about is the vernal equinox, okay? So for example, if we look at the summer solstice on June 21st, then we're going to be asked a few questions about the sun, okay? So we're going to complete the table for the meridional altitude and rising and setting azimuths for these three major paths, right, at these particular dates of the year, okay, for this particular observer at this particular latitude, okay? Note that the rising azimuth and setting azimuth are best determined by dragging the sun in time of day mode with fine-tuning done with the clock and reading the azimuth when the altitude is 0. Let me show you what I mean by that, okay? So let's go ahead, right? Now, getting meridional altitude is not as difficult. Essentially, it will be the highest altitude. The meridional altitude will always be the highest altitude. No matter what arc, no matter what latitude you're at, the sun will take a path that will when it passes through the meridian, that's going to be the point where it is highest in the sky, okay? And so we can see here that if we scroll back and forth and look at the sun's altitude, and we can do that by dragging on the sun, right? So that's one way to control the time of day, right? You're essentially, having, the time of day adjust, right? Go back and forth, of course, which doesn't do in real life. Now, like I said, you can, in here, right, you can do fine tuning. That's because when you do this, you can see it jumps a few minutes at a time, and it's hard to say do 1 minute at a time. It's more like 5 minutes at a time. But if you go and actually click on the hand of the clock, you can easily do, 1 minute at a time, okay? So you can do exactly 1 minute at a time. You cannot do seconds, but you can do 1 minute at a time. And you can actually even type in the time over here and get it exactly to whatever time you want. All right, but if we scroll back and forth, we can see that our highest altitude is at 64.4 degrees, so that would be our meridional altitude. Now we'll have to be a little bit more exact about when that happens in some later parts of the lab, but for now that's perfectly fine for finding the meridional altitude. But as far as the rising azimuth and setting azimuth, those are going to actually be times, okay? Actually, wait, maybe all of these are times. Let me double check. Okay. So yeah, the table for the meridional altitude. Okay, no, they're going to put it. So the rising azimuth and setting azimuth these are all going to be coordinates, right? So none of these are asking for times. They're all asking for coordinates, okay? So here, for example, I've already given you one of the answers. The summer solstice at Normandy, France, would be, at the day of the summer solstice in Normandy, France, at an altitude of, or rather a latitude of 49 degrees north, the sun's highest altitude, which is to say its meridional altitude, would be 64.4 degrees. And that's what you would put right here, okay? But as far as its rising azimuth, well, remember azimuth is this angle measured relative to north. Well, let's see, okay? So let's go and find where it rises, because we know that, the sun rises in the west and sets in the east, and we can make this look a little bit more like that by scrolling around and putting the west on one side, right, and the east on the other, so we get this idea of rising. Oh, I have that backwards. Why did I rise in the west? Wow. No, the sun does not rise in the west, not at all. It rises in the east, okay? And so let's go ahead and actually do something that I think I highly recommend. is turning off the lower section, the underside of the celestial sphere. This is all the stuff that's happening, say on the other side of Earth. And I think it just sort of clouds the picture a little bit. So you can turn that off, and then we can see, this idea that this observer is on a perfectly flat field, and this is what they're seeing. Okay. Now I'm going to bring the sun down, right? So we're going backwards in time, getting to some earlier morning period on this particular day of the year, all right? And we're going to get down to a point where we're going to have the sun set, okay? Or rather have it not risen yet, because we're going backwards in time, okay? Now what I want to do then is find the first point where it's actually going to have a altitude that is positive. Because on the one hand, you can look and say, oh, well, you can tell that the sun hasn't risen yet because our little animation here is dark, okay? And that's okay, but it's not that accurate. The most accurate way is actually look at this value right here that shows this altitude. Now we want that altitude to be exactly 0, because that will represent the moment that the sun is rising. And we're going to do that by now, right? Because I've already, like I said, dragged the sun so I could coarsely get it to the right point. And now more delicately or finely, I'm going to advance time, and get to exactly 0. Okay, right there. Sun has risen. Okay. Now, on the one hand, it's interesting. What time did it rise? It rose at 4:02 a.m. That's pretty cool, right? Wow, that's really early for the sun to rise, but it's a testament to the high latitudes of Europe. Okay, but besides that, also the value that's asked is the azimuth. Okay, now this is the angle measured relative to north. So if I go over here, I imagine some angle, make a triangle that has a point at our observer, because our observer is exactly at the crosshairs or cross lines of the projection of the meridian. So essentially a straight line that goes from north to south, and a straight line that goes from west to east or east to west, and they're right there at the intersection of those lines. So if I made a triangle, right, it wouldn't be a right triangle, but if I made a triangle, the angle is the angle right here that I'm sort of waving over with my mouse. Okay, that is the azimuthal angle, okay, at sunrise, 52.7 degrees. Okay, so there you go. You got another value to put in your table. Now, of course, you would do the same thing for sunset. I'll not give you the exact value, but you can sort of coarsely pull the sun over until you get sort of close to sunset, and then do the fine tuning with the hand of the clock. Now, one thing to point out is that I do say that you're going to do this with time of day mode. What am I referring to there? Well, if you look over here, you actually have an option of how or what dragging the sun actually does, because right now it is in time of day mode. So it says here, dragging the sun's disk changes the ... time of day. But well, sometimes you don't want to change the time of day. Sometimes you want to change the day of the year, and by moving the sun, you're actually advancing the day of the year where the sun is at that location. Okay, I know it's kind of a strange idea, but that's one of the ideas that we're trying to really clear up in this lab. And so if I did that here, right, and I dragged the sun, I wouldn't, be staying at the particular day of the summer solstice on June 21st. Check it out. I'd start changing days, all right? And by dragging the sun, notice that I can't pull it along that line anymore, right? I can't pull it along the ecliptic, or rather, I can't pull it along the declination circle, which is what I was pulling along before. Instead, I'm forced to sort of pull it, in fact, along the ecliptic, which means there's not too much I can do with it at this point. Now, if I say went back to time of day mode and brought it up closer to the meridian at a higher altitude relative to the horizon, and then put it back into day of year mode, then I can actually get quite a bit more control, right? I can actually move it around. But still, you can see that the movement, it's not as intuitive, right? Because I'm almost like pulling it along this, along the meridian, but not exactly, right? I'm sort of pulling in this weird sort of jolting motion, because in fact, it's following a particular shape, okay? Maybe a figure 8, we'll have to see, okay? Now, actually, I just in passing mentioned the name of these circles you can see here. Now, of course, we're only seeing half of the circle. We could see the other half by turning on the underside. So we can see that both the yellow circle and the white circle are complete circles. One of those represents the ecliptic. That's the apparent path of the sun through the celestial sphere. We call it the apparent path because the sun isn't moving, right? It just appears to be moving, relative to Earth, because Earth is orbiting the sun. Okay, hence apparent. But what is the white one then? Well, the white line is the sun's declination circle. Okay, so that's actually showing, I have them backwards, excuse me. The white one is the ecliptic. Okay, so the white one is the ecliptic, and the yellow one here is the declination circle. Okay, so here we're seeing, so the declination circle shows basically where the sun is on that day. okay? The declination that it takes. So on a given day, the sun will follow a declination circle for that particular latitude. Different observers at different latitudes. So someone that's not at Normandy, France, and now we're just by chance we actually went over to practically the next solstice, right? Or rather the next equinox. Okay. Now here we made it exactly the vernal equinox. Okay. So here we are now in the I said vernal. I'm going to say autumnal. So here we are in the autumnal equinox, September 21st. Okay. And I'll try not to give away anything because that is, of course, some more of the answers in this question. But over here, if I was to leave the sun dragging option in time of day mode, then when I move back and forth, it will follow that declination circle. Okay, because that is a circle that's relative to that local sky. Okay, now, right, that's interesting, right? Because of course, when you think about local sky measurements, they're altitude and azimuth, but declination circle isn't, it does change throughout the day, as does altitude and azimuth, but it does represent the arc because of that tie-in between, where we see objects depending on our latitude. Okay, refer to the previous question for more on that, right? That was the purpose of that question, was to explore that idea. Now, the white line is actually the ecliptic, okay? That is the path of the sun. So if we go to time of day mode and we turn off the declination, then that should be kind of where we see the sun should then kind of, will always be on the ecliptic, first of all right? And it's going to be, and that ecliptic will move relative to the observer, right? So the ecliptic will kind of appear to shift at different points relative to the observer, okay? All right, which is kind of interesting what's going on there, right? But again, we'll explore it more later. You're actually going to draw information based on those values. So in other words, since you have 3 points, you have the rising and setting locations, right? Because you're given their coordinates in this hemisphere coordinate system. And you also have the highest point where it crosses the meridian, right? Which is this line, right? Then what we have, and let's go ahead and take a look actually at the meridian. Is the meridian on? Yes. All right, so because the meridian is going to, let's go back to time of day mode. We're of course on October 5th now, so totally different day. But yeah, the meridian is going to be this line right here. Okay, so it looks great. All right, and so then you're going to see, right, so you're going to be able to draw those different coordinates and do your best job of sketching those paths, because you want to kind of show those paths within this pseudo 3D figure. Okay, and then it says here, suppose in question 8 that you are visiting Normandy, France on July 10th. You wake up early and notice the rising azimuth of the sun. In which direction would the value change if you measured it 2 weeks later? All right, so go ahead and try to figure that out yourself and then check if you're right with the simulator. Okay, then we're going to get on to some other information. We're going to get in our first time and really start exploring something more about the path of the sun. All right, so note that the sun can never be at the zenith for Normandy, right? It never actually reaches that highest point. The sun is never directly overhead. Even if we go to the longest day of the year, we go to, June 21st, which it turns out, that's July 21st. If we go to June 21st, which we will kind of show later for any latitude above the tropics, which are these special latitudes on either side of the equator, the Tropic of Capricorn and the Tropic of Cancer. Well, when anything above or below those latitudes, so the northern latitudes or southern latitudes, versus where, for example, all of North America and Europe are all above the tropics, of course. Well, there's never going to be a day during the year where the sun reaches the zenith, right? The highest possible altitude it reaches might be something like 64.4, depending on where you are, right? Now, if you're a little bit lower, maybe you're somewhere like in Mexico or something, then we can have the sun get quite a bit higher overhead. And actually went too far south, but if you're more like in central Mexico, then you might have a point where you could have the sun, get up to maybe 85.3, so pretty close to the zenith, because the zenith, right, is at 90, okay? But still not quite there. And again, this would be, the day of the year where it gets as high as it does, okay? So the longest day of the year corresponds to highest sun of the year, okay? So here, the question asks, where would you have to go and how much latitude would you have to change in order to get to a point where you could have the sun at the zenith, all right? Well, you got to go to the tropics. So hopefully you can figure out how to make that calculation and give your answer there, okay? So moving on to question 10, the figure below shows the approximate illumination of the sun on 2 specific days of the year, all right? So what are the names of these days of the year, right? So notice this is when the earth is tilted as much as possible towards the sun and as much as possible away from the sun in terms of the northern latitudes, okay? So what would be the names of those days of the year, okay? Then question 11, we're going to go back to the figure 8, okay? So this is that same figure 8 that was shown with that special photographic technique of taking the picture of the sun on the same time of day many days, right, over a long period of time, and then overlaying all those images. Well, here we see it again. Here it's actually shown on a globe, okay? Actually, shown on a globe and not arbitrarily So it's actually shown between the tropics, okay? There's a reason for that. And its particular shape, right? It does have that same sort of lopsided figure eight shape with a smaller figure eight in the northern latitudes and a larger one in the southern latitudes, right? What's going on, right? What is that? Well, here's the name of it, right? It's called the analemma, okay? That is, in fact, the name of this figure eight. And what it represents is the sun's apparent path through the sky over the duration of a year, right? It shows the sun's declination for every day of the year, okay? Now, what latitudes does it exist between? Well, I was just talking about that, right? But of course, you can explore it yourself. And then, why do you think the bottom half of the figure eight analemma is so much larger than the top half? Okay. Now, you might want to go back to this question because we will certainly have some more background reading on the analemma later. But if you want to kind of dig into it right now, it's great to think about. And then, what is the significance of the latitude where the figure eight crosses itself? Okay, again, right, we're going to explore that more directly. So we get into question 12, which is the first of our questions where we're going to really start to have some fun messing around with and exploring the analemma. So we're going to set the simulator to the island of Mindanao, Philippines at a latitude of 9.1 degrees, which is well within the tropics, right, near the equator. And, right, cool idea here, if you look really carefully, although it's hard to see in this image of the globe, that actually is where they cross, okay? So 9.1 degrees is that special point where the figure eight crosses over itself, okay? So we'll go ahead and manually set this to 9.1 degrees, all right? And, obviously there's many locations at this particular latitude, but I've chosen one that really exists, right? This particular island in the Philippines. And what we're going to do then is we're going to look at some different times of the year, and we're going to find 2 dates of the year where the sun is as close as possible to the zenith, okay? So you're going to be able to find not one, but 2, and they're going to be quite a few weeks apart. Okay, so don't expect to find them close to each other, right? They're not going to be at either ends of the year. They won't be 6 months apart or anything, but they also won't be, exactly next to each other. So you're going to have to go through, and I would recommend a great way of doing this is actually changing the sun to day of year mode, kind of swiveling it over so you have a good view, and adjusting it around, right? Finding some points where, there across the zenith, all right? Okay, so you have across the zenith there. I'm going to keep pulling on it, okay? And it should be able to make it cross the zenith one more time. And actually, I can do that better by up here, because otherwise, the thing is that it's sort of, because it wants to track that figure eight, what's happening is that I'm not mousing over it correctly. But if I go over here and I just drag through the calendar, then we can see crosses to the zenith, okay? And then it's it reaches the point, turns around, and then crosses to the zenith again on a separate date. See that? Cross, turn around, cross again. All right, pretty cool, right? That only happens at this, particular latitude. All right. Now, as far as getting it exact, you'll probably find that you can't get it exactly to 90 degrees, and that has to do with the ability that we can't control the latitude to, say, 1/100th of a degree, and our limitations of not being able to control seconds in terms of time of day. Okay. Oh, but there was a setting that it says here in question 12 to turn on, and I haven't actually turned it on, and that's going to be show analemma. Okay, so here's the figure eight actually overlaid. Actually, it makes it easier to drag now because now I kind of know how to trace my mouse here, the cursor. And as long as I trace over it, right, I can make the sun follow that path year after year. Okay, because that's what the sun does, right? Now, just a quick idea here, right? Look, if we go to different latitudes, right, then the analemma is at different points, right? Right, yeah, exactly, right? And this is it always represents a whole year. Okay, so it's showing where the sun is going to trace out over the duration of a whole year. And if we go to very high northern latitudes or very, far close to the South Pole, southern latitudes, then some of the analemma is simply never visible. Okay, all right, go back to the north, and we can see, right, that this part of it, this section of the sun's path will just never go above the horizon. So someone at that latitude would never see that part of the analemma, that part of the sun's apparent motion. Okay. Because that's interesting, right? We were talking about apparent motion, this idea of the ecliptic, but this is the next level of its apparent motion. This is its apparent motion in a figure eight. But why? What's actually making the figure eight? Well, that's one of the main goals with this lab, is to go through and explain and get you to understand what's causing it. Okay, so here you're going to fill in this table, taking similar measurements as in the last table in terms of sun's altitude, sun's azimuth, at a very particular time of noon, right? So you want to keep that time fixed, okay? So, if I just go back to that real fast, go back to 9.1 in terms of latitude, north, then you want to turn this exactly to noon, and you're not going to vary it, okay? But then in question 13, then you're actually going to look at different latitudes, and you're going to find the time of the day where the altitude is exactly 90. Now, I found some very specific latitudes where you will be able to get the sun to hit exactly 90, okay? And you'll be able to get the sun to hit exactly 90 2 days out of the year every time, okay? But here's the difference, because I said, I might have misspoke a second ago, but I'll explain. There's something still very significant about 9.1 degrees north, that particular latitude, and such as the island of Mindanao, Philippines. And that's because the sun passes through the zenith twice a year, okay, which it also does at all these other latitudes because they're all within the tropics, okay? And that's how you're going to complete the table. But what's special about 9.1? It passes through the zenith twice a year at noon. Okay. Now, again, we're not going to be able to get it exactly because it's not exactly 9.1. It's going to be 9.1, and then there's a certain number of arc minutes and arc seconds to get the exact latitude where you have that point on Earth where the sun passes through the zenith at noon twice a year. Okay. But at all these other points, you will be able to get the sun to hit exactly 90 degrees, but at different times of the day. Okay. So that's where you're going to have to control here. And let me just show you one so that you can make some sense of this. Okay. So let's go ahead and choose, let's do, what's a good one, right? Because we got the first three are south, and then actually we have four of them that are south, right? So basically one that's almost all the way out of the tropics, right? 22.5, right? Because about 23.5 is the end of the tropics. That's the last point where the analemma reaches, right? That would be the extremes of the analemma. If we go back here and take a look at it, yeah, we're still in, so take our view. Essentially, if we're seeing this on the globe, one end of it, one extreme point of the figure eight is at the southern end would be at the Tropic of Capricorn, and then the northern end would be at the Tropic of Cancer, okay? Which is why where the figure eight crosses is in the north, because obviously, the tropics are exactly, equidistant from the equator, but the figure eight is not symmetric, okay? Why is it not symmetric? Very interesting, right? But let's go ahead and do the 10.3 degrees south, okay? So go over here. Now the way to do this, because it doesn't actually let you control south, is if you just go into any southern latitude and then double click on it, then it will stay in the southern latitude. So 10.3, I locked it to 10.3 degrees south. Now here I'm actually going to vary the time. So I probably want to actually put this back in time of day, okay? And let's see, maybe. So we want to, because we want to get it to a particular point, and then we want to find the day of the year and then the time of the day. So it's a two-step process. So probably the best way to do that is to leave it near noon, and then find the day where we're going to get that near the zenith. So let's kind of go around here. So we can see, and having the analemma, having this red trace is very, very helpful, because if you just go through the year, right, you can see, okay, well, this is where it crosses, this east-west line. And so all I need to do is just move that, that red part of the arc of the larger part of the figure eight, the larger part of the analemma, the southern part of the analemma. All I want to do is just move it a little bit to the side, so that it's actually going to take this red line and move it over to this intersection, which is the zenith, okay? Exactly where, the directly overhead point is, okay? So how would I do that? Well, I do that by adjusting the time, see? So if I adjust the time by going back in time, I can get one side of the analemma to hit the zenith exactly. And if I go the other way, sometime past noon, I can get the other side to hit it. So that's going to give me an idea how many minutes, ahead of noon or behind noon it's going to take at different days of the year to actually find, the sun exactly at the zenith. Okay? Okay. Can I get an idea? All right, so let's go ahead and find a time then. So I'm going to then again start advancing the date. I'm going to bring it over and try to get it right up to an altitude of 90. All right, so bringing it up. Okay, so that didn't quite hit it, right? Because it got up to 89.9, right? But didn't quite get there. So let's go back to 89.9. Okay, and then let's change the time. Okay, 89.9, 90, exactly. There we go. Okay, so February 21st. Okay, that's what you put right here rather, because we're at 10.3 south. So February 21st is the day of the year. The time of the day, okay, would be 12:14, not noon. Remember, because that's only possible at a latitude of about 9.1 degrees north. Okay, All right. And then, but the latitude is fixed. That's the whole point, right? It has to be this number. Then you're going to record its azimuth, its declination, and its right ascension, which is all this information you can record right out of the simulator. Okay. Okay. Then you're going to go to the other day of the year. Okay. At that same latitude and different time of the day. All right. Kind of see what I'm saying here? So and probably the best way to do that is to go, right, pull the analemma so that it's got the red line crossing exactly over the zenith. See, because there it hasn't gotten to it. But if I go over here, it gets right to the zenith. If I continue to go, earlier than noon, then I would overshoot it, right? So instead, I want to have the intersection be right about there. Okay. And you can fine tune that as you need to. And then I'm going to find a date, okay? And you can see I probably have to go, way actually pretty far forward in the year, all right? All the way up to like October or something, all right? And then find a date where it's going to get to that point again, all right? And you can see that this isn't exactly right because it's 89.9. So you're probably going to have to either adjust the date or the time to get it just right, okay? But I made sure that all of these, based on the limitations of the simulator in terms of its allowed precision, will give you exactly values of sun's altitude for some day of the year and some time of the day, okay? Now, why do we care about this? Well, you can see it's going to allow us to just really understand what the analemma is telling us, okay? So in question 14, it says, based on the dates you have found, okay, in the tropics, as the sun reaches maximum altitude in the local sky on the solstice, the summer solstice for the northern latitudes and winter solstice for the south, explain how you know, okay? I don't want to give that away too much, right? Really think about what you saw. Did the sun reach its maximum altitude, which after all is the zenith? You can't go any higher than the zenith because that's 90. It is impossible. There's no 91, okay? So did that happen on the solstice? Yes or no, right? Because that's going to give you your answer, okay? And then, right, then we're going to go and consider if this means that the solstice is not actually the longest day of the year for these tropical latitudes. So we're going to go back and look at some, particular examples. We're not going to look at all of them, but we're just going to highlight just two particular ones. So 10.3 south, which is actually one of the ones we were just looking at, right? I forgot that was one of the ones I decided to highlight. And the one in the north, 12.8. And these are ones that are from the table, okay? And here you're going to look at the dates when the sun reaches the zenith, right? Those are the dates that from the previous table, you're just going to reproduce them from the table in question 13. So they should show up in that first column in question 15. Then you're going to put the time of the day of the sunrise and the time of the day of the sunset. Okay, so those are going to be the exact times. Then you're going to get the length of the day, okay? Hours and minutes. Cool, okay? Then, right, because those are literally, and there'll be two values, okay? So you're going to have the length of the day on 2 different days, the 2 days where the sun passes the zenith, right? So there should be two values on every one of these, okay? And I didn't actually kind of create split rows within here. So just make sure that you have, that you leave space to put 2 values in each of these cells, okay? For, so, and every one of them. But then in the next table, right, now you're gonna, use this to answer the question, okay? Because then you're gonna go to the solstice, okay? In the one location that was in the south, the 10.3 degrees, that its longest day of the year, we would think, right, in terms of the meaning of the solstice, is December 22nd, okay? Oh, actually, I'm using the 22nd here. I thought I started using the 21st, but I think the simulator suggests using the 22nd. So you're using December 22nd for the winter solstice, and then we're using June 21st for the summer solstice, which should correspond to the longest day of the year in the northern latitudes, okay? Now, then again, you're going to take the same sort of measurements, max altitude, which is going to be something less than 90, because we know that the 2 days where it reached 90 were definitely not, the solstices, respectively north or south, okay, or respectively, winter and summer. And then you're going to get the time of the day of the sunrise, or time of the day of the sunset, and then the length of the day. And then comparing the answers between the length of the day on the 2 days that the sun reached the zenith for both these latitudes, and the length of the day on the respective solstice, you then will be able to answer, right? Is it true then that the longest day of the year is no longer the solstice in the tropics, right? Well, you're going to find out. It's going to be pretty cool. All right, but then you're going to go for a minute and go back to the non-tropics, right? Where most likely you live, right? I live in North America, and certainly it's we're used to a particular path of the sun where it never reaches the zenith. Okay, we're well above the tropics. So what does it mean for us, right? Well, let's consider some point, right, for a 0.45 degrees north, right, so kind of like Europe, and some 0.45 degrees south, maybe something like Chile or South Africa or something, right, or parts of Australia. And what we're going to look at then is we're going to look at the max altitude of the sun on other days of the year. Okay, so we're going to look at it specifically on the solstice, okay, find its max altitude, and then look at just 4 other days of the year that are sort of evenly spread apart. Then we're going to look at the length of the day, right, on other days of the year, right? Well, first of all, at the solstice, okay, and you do that the same way. So this table doesn't have as much detail because I assume you've already got familiar with the technique of measuring time of sunrise, time of sunset, and then taking the difference between the two in order to calculate the length, because that's what you're going to have to do every time it asks you to calculate the length. Okay, you just don't have to show your steps. Okay, so here you're going to have the length of the day, right, at these particular latitudes and longitudes, or rather latitudes, just latitudes. Okay. And that's going to be, so day length of the solstice, and then here max altitude at the solstice. Okay, so this table entirely max altitude values, this table entirely day length values, and then you're going to summarize information in the from the tables by answering the questions below. Did the max altitude of the sun that you found show that the solstice was the day with the highest altitude sun for these latitudes? Did the longest day of the year also occur on the solstice? Interesting, right? Because we know for sure that the highest altitude does not correspond to the solstice within the tropics. Now, you will at this point also know whether or not the longest day of the year also doesn't correspond to the solstices within the tropics. But then you're going to then go back to these non-tropical latitudes and see what the connection is. Okay. So then, in part B, it says, in general, would you say, it should say, not saw, would you say that there are two different sets of rules for the solstices, one that applies to the tropics and one that applies to latitudes above the tropics? What is the one rule about the solstices that seems to be true for both regions? What am I hinting at there? All right. And then what is the significance of the altitudes of the analemma at these different latitudes? To help answer this question, consider this fact. The altitudinal spread of the analemma is caused by the axial tilt of Earth, right? That 23.44 degrees, or approximately 23.5 degrees. Interesting stuff. All right, we're almost done. So question 17, now turning your attention to the far northern and southern latitudes, and set up the simulator for Nordkapp, maybe, right? I shouldn't have tried to pronounce that one either. Norway, which has a latitude of 71 degrees north, is certainly one of the most extreme latitudes we've seen so far. By far, actually. Complete the following chart for the meridional altitude and the rising and setting azimuths. Okay, so this is going to be very much like one of that earlier question, and you're going to actually trace the paths here. Okay, then note that the sun doesn't rise every day from this location. How far would you need to move on the Earth to find the latitude where the sun does rise? Kind of similar to before, where we asked, how far would you have to go in terms of latitudinal distance, right? In terms of angles. How far would you have to go from Normandy, France, to a point where the sun reaches the zenith? Well, same sort of thing here. How far would you have to go to make sure that you have every day of the year have some sun, right? Because of course, in the far north and far south, you have these days with no sun, which means you also have days with no darkness, right? Then question 19, what do you notice about the altitudes of the analemma for altitudes where the sun doesn't rise every day of the year? Well, I already kind of gave that away when I talked about the extreme latitudes and what happens to the analemma relative to the horizon. Okay, so that's what the question 19 is asking about. Now, finally, the last few is we really dig into some background information on the analemma. We look at this graph that actually shows it at different dates, showing its declination values as well as declination and altitude. Okay, so this is so we have here, azimuth and altitude. So this is the location of the sun over different days of the year, and this is for a specific location. This is this figure corresponds to a latitude of 51.5 degrees. Okay, so this is what the analemma looks like at that latitude, 51.5 degrees north. Okay, and these are its locations over the year. All right, and this would just be in terms of the local sky measurements, altitude, and azimuth. Okay. And then what you're going to do is you're then going to go on and go to that latitude, and you're going to look at a number of different days, okay? So you're going to go through and fill out the sun's azimuth, the equation of time, and the sun's declination. Because it says here that the equation of time is very, very closely related to the azimuthal spread of the analemma. In other words, this idea, the equation of time, which I know is a crazy term, it actually refers to just how wide the analemma is, okay? And so by azimuthal spread, I'm essentially referring to its x values, right? If this graph is x and y, right? Y for vertical, x for horizontal. So azimuthal spread is just how far it moves along this horizontal axis. It's x-axis, okay? Interesting, right? So what's going on there, right? Why is there this equation of time that corresponds to the the spread of the analemma, which is the apparent strange figure-8 shape of the sun? Well, it all has to do with these intricacies of Earth's orbit. But before I even get into that, the cool idea about this table right here is to really ground you into showing you what the equation of time is. Because actually, it's not really an equation at all, and you will just be pulling the value directly off the simulator. So for example, if we just do one over here, so it doesn't seem too abstract to you, let's drop in 51.5 degrees north. Oh, it's still in the south. See, like it won't go to the north unless you're already in the north. Let's do 51.5. All right, and then we'll leave the analemma on just for the sake of visualization, and then we're just going to go to different dates. So we'll go to January 1st, right? So I'll go over here. Okay, January 1st. All right, and then we want to set the time exactly to noon. All right, so just pull the time up to exactly noon. All right, so 12 o'clock. This is a 24-hour clock, so there won't be any confusion about whether this is 12 a.m. or p.m. Right? So this is noon, right? 12. Okay. Right, as opposed to 2400, right? This is 1200. And then we're just going to read off information. Sun's altitude, 15.5. Sun's azimuth, 179.1. All right. And then, let's see. Actually, it didn't want the altitude. Just wants azimuth, right? And there's a reason I asked these particular values. And then equation of time, right? So equation of time is right over here. -3 minutes and 43 seconds. Okay. So the equation of time is always in minutes and seconds. And it's either negative or positive. Okay. Okay, and then sun's declination. Okay, so where's the sun's declination? So that's gonna be right over here, -23. Okay, all right. So those are the values you want: azimuth, equation of time, and declination. Now, why do you want them? Because, as I said, the whole idea is to take the obscurity of the equation of time and make it seem less strange, right? Make it seem less opaque, less esoteric, right? Because really all it is a correction. And it's telling you that on certain days of the year, you're essentially ahead of solar time. On other days of the year, you're behind solar time. And it's a matter of, going back to the simulator, it's a matter of whether you're on this side of the analemma, where all of the corrections are positive, all right? That's because you need to add time because you're behind solar time, right? And this is relative to the meridian, see? So relative to the meridian, if you're on this, this section of the figure eight, or up here, this smaller section, you're gonna have positive equations of time because you're behind the meridian, so you have to add time to get to actual solar time. On the other hand, if you're on this side of the analemma over here, because now you're to the east of the meridian, or if you're in the dates that correspond to where the sun is on this wide section of the analemma, you're in front of the meridian. Therefore, your equation of time is negative because it represents the time you have to subtract to get back to true solar time. Okay, so what's going on there, right? Why is that? Why do we have this correction? And why is a correction called the equation of time? Well, I read that the actual term here, equation of time, is referring to what's called the medieval definition of equation, because back 500 years ago, when people used the word equation, that actually meant correction, all right? But now we call it, the time correction or something, okay? And actually, in maritime terms, there actually is a more kind of everyday name for it. I think it is just called something like the time correction, right? But the equation of time is a term that has stuck around in astronomy, so we still call it that. But all it is a correction. It's how many minutes you need to add or subtract to get to true solar time. Okay. Now, what's going on there? Why do you have to do that? Well, the idea is all because of Earth's orbit. Because Earth's orbit is not perfect, as in it's not a perfect circle, and the axial tilt has a certain consequence. Now, one thing you're going to do, you're actually going to plot your equation of time values versus sun declination on the graph below. Okay, so what you're going to do is you're going to get the equation of time values and the sun's declination. So these are going to be your 2 points. Okay, and the one that's going to be your horizontal coordinate is going to be the equation of time. So that's the column that's further to the left, and then the column that's further to the right, the sun's declination, that's going to be all of your vertical values. So you're literally just going to read them off of the table. All right, so read off equation of time and sun's declination, and just plot all the ones that I gave you. And what shape you're going to get? You guessed it, you'll actually get the figure eight, okay? Because that's what the equation of time is actually creating the analemma. They're essentially two names for the same thing, which isn't that big of a mystery if you go back, or if you're paying very close attention to that image of the globe, because on the globe, it has this little section here that actually shows, I'll scroll over a bit here, it shows the clock ahead of the sun, clock behind the sun, right? It's got an actual scale here that corresponds to the width, the azimuthal spread of the analemma, and it even says here, scale of time, right? That is the equation of time, All right. So in other words, the equation of time is just how wide the analemma is. Aha, pretty cool, huh? All right. So that's what you're going to actually plot out here in the graph. All right, so back down to there. Then I have some more background information, right? So we saw that really, kind of like information heavy, but very interesting video at the beginning. Well, there's some really neat web pages that I have some links to here. So let's go ahead and take a quick look at that, right, as we wrap things up here. So this is the page actually called the equation of time, all right? And the one you're gonna be looking at is the components of the equation of time. That's primarily what you want to look at. And the figures actually that I've included here, this figure shows the eccentricity effect and the obliquity effect. This is the two of the three major components that actually create the equation of time. The reason that sometimes we're ahead or behind of this solar time, because the thing is that the real sun isn't exactly where we expect it to be. So we have this idea that we've corrected for from the sidereal year to the tropic year, right? The tropical year, right? We said we've corrected for the fact that we're moving around the sun, but the fact is that just making that correction is not enough, because that assumes that we're moving in a perfect circle, and it assumes that our axial tilt isn't going to change any of the apparent velocities. But the reality is that both those effects, the axial tilt, which its effect on the length of the day, right, or and the difference between solar time and real time, is called obliquity. And then the other effect, the effect that Earth's orbit is not a perfect circle, it's in fact an ellipse, that's the eccentricity. Okay. And here are just some figures that summarize all that, but there's some really nice animations that you can look at here. So one that I thought was particularly good is so this one just shows the obliquity effect, all right, which is this creates actually a sinusoidal effect, all right. And then this one, there's one that just shows the effect of eccentricity. Let's see. So, yep, following the sun. Oh, this is the eccentricity effect. There it is. And then here's and then there should be one that just has the obliquity. Right, here's just the obliquity effect on its own, which is also a sine wave. All right. And then when you combine them together, you get the equation of time, which is just the composite of these two sine waves, but which are out of sync with each other and have different amplitudes. And the overall effect is this weird shape, right? And that's the figure eight. So this shape that we're looking at, this is actually, if we like trace it out on different coordinates, that actually makes the figure eight. Which I know, I mean, that's a bit to wrap your head around, but that's where the figure eight comes from, is exactly tracing out this sum of two sine curves. Okay, and you can see here that we're looking at, over the duration of a year, the location of the true sun, the dynamic mean sun, right? The projection of it, the civil mean sun. We're looking at key points like the equinox and the solstices, as well as the aphelion and the perihelion, which refer to the furthest distance the Earth is from the sun, which is the aphelion, and the perihelion, which is as close as the Earth gets to the sun. And also the 1st of January, so to show the start of every year. And right, we can see this combined effect tracing out the equation of time. All right, by just having these two combined effects of eccentricity and obliquity. Obliquity is hard to kind of wrap your head around, but it has to do with the fact that the Earth is tilted, and because of that, sort of the motion of the sun appears to be either kind of more dramatic or less dramatic, whether we're viewing it tilted back or tilted forward. Okay. All right, and here is, again, everything in summary, showing the equation of time. Here are the figures that sum it all up. All right, so hopefully that, is interesting at the very least, and certainly the lab, strives to have you make sense of some of that. Okay, so I'll zoom out a bit, and then we'll just go scroll down. I have a couple questions that ask about kind of understanding that, as well as just basically interpreting the graphs. Okay, then finally, there's actually one last simulator you're going to look at, which is on this. Well, there's some background information and then a simulator within that page. And this is to speculate on how things would be different if Earth, say, had a perfectly circular orbit instead of a slightly elliptical one, because this is the eccentricity of Earth's orbit. Not very large as far as eccentricities go, because our orbit is fairly circular, but not perfect. Okay, and what if it was perfectly circular, right? Or what if we had zero axial tilt, right? How would that change the shape of the sun's apparent path through the sky over the duration of a year? Okay, because it certainly would change the shape. And so we'll go over here, right? This is all within this page here. And let's see, here's the overall page. It's actually called analemma.com. These websites have great names, equationoftime.info and analemma.com, right? They're obviously, the main pages for these topics. Right? This shows another good example of a globe with the analemma on it. I've heard that a lot of times they put these on the globe because otherwise there's a lot of dead space in the Pacific Ocean. And it looked kind of boring. So you might as well just put the analemma in there. But it also, has a lot of scientific significance. Okay, not that people really probably understood it most of the time, but still looked cool. All right, but anyway, moving on, right? So here is, one of the big causes of the shape of the analemma, all right, in terms of its azimuthal spread. And here, right, which is called the obliquity. And this actually does a good job of explaining it. I think this video is definitely worth checking out. Here's the eccentricity, which is the idea that Earth's orbit is not a perfect circle. All right. And then the last one, which we'll see in the very last question, question 22, which is something called the apse angle, which I haven't mentioned yet because it doesn't actually affect the equation of time. Okay, so the apse angle has no effect on the equation of time in terms of the actual spread of the analemma, but it does create a skewing effect. Okay, so it is considered the third major factor, but again, it has no effect on the on the number of minutes you add or subtract. It just creates a skew, so the dates would all shift. Okay. And then you put everything together, and then you can kind of get the overall understanding of the equation of time, all right, as well as the particular shape of the analemma. And that comes about here. If you go to other, it will show you, talk about the analemmas of other planets and even show you some great videos for them. But the simulator, I think, is one of the best ways to explore that. And I don't want to give away the answers here. And as far as the parts A and B of question 21, it asks you to speculate about them, and I would love you to think about it first, right, before you go ahead and run it in the simulator. But let's go ahead and look at a planet that let's go ahead and look at Mars, right? So this is Mars's analemma, right? It's not a figure eight. Wow, why is that, right? What is going on here to make it not a figure eight? Well, that's pretty cool, right? Well, what about, say, Saturn, right? Saturn is technically a figure eight, but almost has no top section, right? I think Jupiter is also just going to be basically an ellipse, okay? You can look at, now Uranus has one that is a figure eight, but it almost looks more like an hourglass. Wow, why is that? Well, look at this value here, okay? Now, remember, what does this value represent, right? This value here represents the actual tilt angle, right? So here, this Greek letter epsilon, that's the tilt angle, the one that this simulator uses for the tilt angle. You can actually see it here in the picture too, because Uranus is often described as being tilted on its side. All right, we can look at Neptune. Neptune has a figure eight that actually looks a lot like ours, but then again, the values are kind of similar, all right? So, that's a good way to kind of, not give away the answer, but show some examples that, certainly, show a bit. And then finally, question 22 does refer to that apse angle. I have a figure here that shows what it is because it's the angle between the solstice and the perihelion. Okay, so within the orbit of Earth, the angle between those 2 points in the ellipse, that's the apse angle in degree. Okay, and you can actually control that within the simulator. So if you go back, let's go to some arbitrary planet like Mars, right? So what if we change the apse angle? It changes the shape, and it can actually even turn this, right? This, kind of teardrop shaped, I think that's what it's often called. So this teardrop shaped analemma of Mars, you can turn it into a figure eight by just adjusting the apse angle, okay? Just adjusting the angle between those 2 points, the perihelion and the winter solstice, okay? Now ours are pretty close to each other. We have a small apse angle. So if you go back to Earth with the default values, right, our apse angle is at 12 degrees because those 2 points are not too far apart. The winter solstice closely corresponds to the perihelion, okay? Which is kind of interesting that we're closest to the sun in the winter of the northern hemisphere, right? What does that mean, right? Well, the video actually speculates on it a little bit at the very beginning of the lab, but overall it doesn't seem to have a dominant effect on our climate or anything. But regardless, right, that we have a small angle, but if we vary it, we can change the shape of our analemma. But we don't change the overall spread, okay? All right, we don't change the actual magnitude of the width. All right, so that summarizes or wraps everything up. I hope this, this in-depth and intriguing lab is worth your time, and I hope you find it as interesting as I did, and I hope this video has been informative and helpful. Thank you so much for watching.